Hey there, and welcome. Today, we're going to explore a really beautiful idea from computer science. It's all about taking something that looks, well, kind of tangled and messy, and finding the clean, simple process that's hiding inside. It all starts with a question you've probably never even thought to ask. When you hit Control F to find a word in a huge document, how on earth does it happen so fast? It feels like magic, right? But behind that speed is a very clever and actually very simple kind of machine. So let's meet the hero of our story, this pattern matching machine. It's a really foundational idea in computing, especially when we're talking about finding specific little bits of text inside a whole sea of characters. Okay, so it has a pretty intimidating name, a Deterministic Finite Automaton, or DFA for short. I know it sounds super academic, but let's just break it down. Finite just means it only has a limited number of states it can be in. And deterministic means that from any state, if it reads a character, there's only one single predictable place it can go next. No guessing games. It's just a simple little machine that chugs along one character at a time. Let's look at a super simple example here. This little diagram is a DFA that's built to do one thing and one thing only. Check if a string of text has exactly one B in it. See that state on the far left? That's our starting point. If we read any character that's not a B, we'll just hang out in that state. But the moment we see a B, we follow that arrow to the middle state. That one with the double circle. That's our accepting state. If the text ends right there, we've won. But what if we see another B? Well, then we follow the next arrow to that state on the right. A trap state it can never leave. It's really just a simple flowchart for reading text. So that little machine is great for finding one simple pattern. But what happens when we need to find, hundreds of different patterns all at the same time? In the real world, things get messy. Take a compiler, for example, the program that turns code into something a computer can run. It can't just look for one thing. It needs to spot all the different pieces of a programming language. Keywords like if or for, operators like plus and minus, all of it. So the challenge becomes trying to build one single, unified machine that can recognize everything at once. And if you just try to jam everything together without a smart strategy, well, as our source material says, the complexity of such a task becomes enormous. You just end up with a big, inefficient tangle. And this diagram really shows you what that tangle looks like. Here, we're trying to build a machine that can tell the difference between similar patterns, like the less than symbol versus the less than or equal to symbol. As you add more and more of these related patterns, the whole thing just explodes with new states and connections. Now imagine scaling this up for an entire programming language. You get this massive, clunky machine that's just a nightmare to work with. So how do we fix this? How do we untangle that mess? Well, this is where the really elegant idea comes in. The key is to look for states inside our machine that are basically doing the exact same job. We can think of them as hidden twins. The technique is called state minimization, and the core idea is actually super intuitive when you think about it. If you have two states in your machine, and no matter what text you feed them from that point on, they lead to the exact same result, then for all practical purposes, they're the same state. There are twins. And if they're twins, we can just merge them into one without changing what the machine does at all. The official term for these twins is indistinguishable states. And really, all it means is that you can't come up with any string of characters that would prove they're different. If every possible future leads them both to a win or both to a loss, then they're basically the same thing. So how do you find these twins? Well, the process is this clever game of splitting groups. First, you just make two big piles, all the accepting states in one and all the non-accepting states in the other. That's your first guess. Then you start testing those piles. You pick a character, say the letter A, and you ask, for every state in this pile, does the letter A send them all to the same new pile? If the answer is no, if some go to pile X and others go to pile Y, then you've just found a difference. So you have to split that pile into smaller ones. You just keep doing this over and over until you can't find any reason to split any of the piles anymore. And whatever states are left sharing a pile at the end, those are your true, indistinguishable twins. And here is the beautiful result. On the left, you can see that states 2 and 3 are indistinguishable. No matter what comes next, they behave in the exact same way. So we can merge them, and we get the much cleaner, simpler machine on the right. It does the exact same job, but with fewer parts. Now that is what we call computational elegance, getting the same result with less complexity. Which, of course, brings us to the big question. This is all very neat, but why does this kind of elegance actually matter in the real world? A smaller machine is definitely prettier to look at from a theory perspective,
But does that really make it better for the programs we use every day?
Oh yeah, absolutely. Take a look at this. The magic of any DFA, big or small, is that it runs incredibly fast. That's the whole point. But the huge advantage of minimizing it is that we get a much smaller, more compact machine. That means it takes up less memory, and it's often faster to build in the first place. So we get that same lightning-fast performance, but in a much more efficient little package. So this isn't just some abstract exercise. It has a real impact. Using less memory and having a cleaner structure means that the tools we rely on, compilers, text editors, you name it, can be faster and leaner.
At the end of the day, state minimization is just a perfect example of elegance in computing. It's about finding the true essential structure of a problem and just stripping away all the extra noise.
And this idea, this search for the minimal, most essential version of a solution, it's a theme you see all over computer science. It's a little reminder that sometimes the most powerful approach isn't a more complicated algorithm, but just a deeper, calmer understanding of the problem itself. Thanks for exploring this with me.